It seems like I got my second surge of motivation right when everybody else lost theirs.
Are you motivated?
I don't have any other choice at this point.
Yeah, I get that.
Okay. All right, we're recording. Okay, now, so in case it's relevant to anyone else, Taylor's theorem for polynomial degree 2 for a given function g of x, if it's centered at 0, then this is what you would fill in.
And then in turn, T3 would be, well, I mean, if you had the Taylor theorem, like Taylor probability.
That would be the next term.
Yeah, B1 triple
Zero.
X.
Cubed, and here, so it's generally okay. I'm like double digit people here, so x is generally x minus the center to whatever power is set. In this case, the center is 0. All of the derivatives are evaluated at whatever the given center is. Yeah. Okay, now back to vector land. There's a couple examples from last time that are related to homework problems, so I want to have those. Ready. Okay. Those some examples. So we're given a vector R, which has components Rx and Ry, so both the X and Y component. And for this example, components are 40.7 and 18.3. Okay. In the homework, this vector R is referred to as a resultant. That term doesn't actually mean anything as far as how the homework problem is done. The term comes up, for instance, actually the example I did last time where I had the plane, I had the velocity vector for a plane indicating its airspeed, but I had another vector for wind. So then I add those two together to find the course of a plane and its ground speed. That vector is referred to as a resultant. So when you're adding two vectors together, depending on the application, that vector is sometimes called a resultant. I'm only mentioning that because if you see the term somewhere, that's what it's referring to. Okay. Now, what we're supposed to do with this vector is find the magnitude of R and the angle theta that it's also referred to as the direction of a vector. So the idea is, and I'll try to draw this scale as best I can. This is your vector R. So the length of this is the magnitude of R. That's one thing. And then you're also tasked with finding this angle theta that the vector makes with the positive x-axis. And I gave a formula for this last time, but I wanted to see if it's worked out in an example. So the magnitude of R, that's the square root of a sum of squares of all the components. So you go ahead and plug in those components. 40.7 for X, 18.3 for Y. And then that is roughly 44.6. And again, numbers don't work out nicely. Now, what about theta? What's the equation this came up last time? The equation for theta. Yeah, okay. It is arctangent of y over x, but how come that's correct in this case? It's not always correct.
Positive,
What?
they're all positive.
Yeah, and the main thing is x is positive. X being positive alone is enough. No, this is what you do. All right, so it's arctangent of 18.3. Make sure the y goes on top. In your fraction, and this is 2.22 radians. Okay. Right. That'll be equivalent to, wait, that's wholly not right. That'll be the wrong number for my notes. 0.42 radians. But that is equivalent to 24.2 degrees. So a problem might ask for your answer in either radians or degrees. Okay. Maybe that happened to you in whatever class where you needed to use a calculator, where you needed to do some trig, and you got the wrong answer, or maybe even ended up losing points because your calculator was in the wrong mode.
Yeah.
Radian versus degree.
Yes.
Yeah. So if you're supposed to be in radians and but your calculator is actually in degree mode, then you're always going to get a cosine value that's near 1 or a sine value that's near 0. Because when you're dealing with radians, generally those are pretty small numbers. So if you mistakenly interpret those numbers as degrees, you're talking about sine of something near 0, cosine of something near 0. So I mentioned that because that could be like a tip off that you're in the wrong mode. When you're too freaked out, test anxiety to actually look at the screen. Right, so any questions about this one, finding the magnitude and direction? All right. One more. Time vector is -6, -2, asks for the same thing, magnitude and direction. So for you, just take square root of the sum of squares.
Then a 7 or 2.
That's a 2. So we get the square root of 40 for the magnitude, but what about what's theta going to be in this case?
Would it be tan x over y or arctan x over y?
There's more. We start with that. But there's something more that has to be done in this case. I can't, I don't remember from last time.
Plus pi.
Plus pi. If you wanted in radians, which actually this example does call for, because the x component is negative.
So if you wanted degrees, you wouldn't add the pi?
You would add 180 degrees.
Oh, okay.
Yeah, so you add whatever is correct units. Okay, so then we get roughly 3.46 radians. Okay. If we look at the vector, so x is -6 and the y component is -2, so that's roughly something like this. And sure enough, the angle that the vector makes with the positive x-axis is a little bit past pi. So 3.46. Sure enough, is a little bit past pi. Yeah, and so when the x is negative, you can expect the angle to be somewhat larger. Just because of we're looking at the angles made with respect to a positive x-axis, but a negative x is gonna put you way over here. So if you go for this whole process and you see that you get a small angle, that means you forgot to add the pi or forgot to add 180 degrees. So any questions about these examples? All right. Now, they will look at a new vector operation. Well, it might not be new to you. May have seen it like in a physics class. But it's, when you add vectors, you add them component wise. Say with subtraction, we don't really have the notion of multiplying vectors, but this operation kind of is. We're actually going to see two operations that are referred to as a product. But the dot product today, and then the cross product next time. Okay. Now the dot product has quite a few uses, but the use I'm going to focus on right now to introduce it is, suppose you're given two vectors, I'll call u and v. So we have some angle between them, theta. So problem is this, given these vectors u and v, what is the angle between these two vectors? Okay. So to answer this, we're actually going to recall something you've had a chance to forget about from trig. So if I draw in the vector starts at this point and ends at this point, so I'll call this vector W. So what we have is U plus W is equal to V. So the law of triangles is that U plus W is equal to V. So then I can just rearrange that and find out what W is. The W is equal to V minus U. Then I could use from trig the law of cosines that relates the sides of all three sides of this triangle. So you can think of it as a generalization of the Pythagorean theorem. The law of cosines says that the length of this side of a triangle that is opposite the angle theta, so magnitude of V minus U, is equal to the sum of squares of the lengths of the other two sides, if I need square there. Okay, so this looks Pythagorean theorem like, but because this is generally not a right triangle, I need to add on one more term, that is minus 2 magnitude of U, magnitude of V, times the cosine of the angle between them. So that's what the law of cosines tells us, how does all three sides of a triangle relate to each other. Now, I'm going to write U and V in terms of their components. Now, even though we have a two-dimensional drawing, we'll just assume that this is happening in three-dimensional space. So U and V have three components, U1, U2, U3. So these are the X, Y, and Z components of U. And then we have V1, V2, V3 are the X, Y, and Z components of V. I'm not gonna go through all the algebra here. But if I were to express all of these vector magnitudes in terms of the components, so we have, for instance, the magnitude of U squared is square root of U1 squared plus U2 squared plus U3 squared and so forth. So if I fill all that in here, so we write U and V throughout in terms of its components, then this is what I get. I have U1 V1 plus U2 V2 plus U3 V3 is equal to the magnitude of U times the magnitude of V times the cosine of the angle between them. So it all simplifies to this. So what do we have here? We are multiplying corresponding components of these vectors. So you multiply the X components, the Y components, Z components, add them all up. So what we're going to do is define the dot product by the way, it's also known as the inner product of U and V. Following. So assuming U and V have these components, the way to write a dot product is U and then a big old dot V. And we have, for what I've just done, two formulas for it. So the most straightforward one is this one where you multiply corresponding components and add them up. But for what we have down here, that happens to be equal to product of our magnitudes times the cosine of the angle between them. So you can use either formula to compute the dot product depending on what information you're given about the vector. Are you given its X, Y, and Z components, or are you given magnitude and angle between them? I'm going to show you examples of how to use this, but first, any questions about what happened here? Yeah.
Geometric intuition behind it, like some sort of a geometric interpretation.
Of just dot product in general. Okay. Well, I'm thinking about something I'm going to be covering a little bit later today. Well, one way to think of it, especially if, for example, if suppose V is a unit vector, then U dot V is the, you think of it as a component of U in the direction of V. In other words, how much is V contributing to U? The dot product can tell you that. So for example, suppose the dot product is 0. That happens when the vectors are perpendicular. So yeah, or orthogonal. So V is not contributing to U at all in that case. Yeah. Some things I'll talk about a little bit. We'll talk about again. Okay. Any questions? Yes.
Where are the -2 go?
Yeah.
Yeah, I was kind of thinking.
Okay. A lot of algebra happened to get from here to here. what, okay,
We're not gonna need to derive that our own though, like we just need to know that bottom equation.
okay, you do not need to know where this comes from, but I will tell you where the -2 went. Okay, because what happens is, if I plug in these components over here, then, u minus, v minus u squared would be equal to the sum of squares of differences of all the components. We have v1 minus u1 squared plus v2 minus u2 squared plus v3 minus u3 squared. And then what happens when you expand this? I'll just do the first one. v1 squared minus 2 u1 v1 plus u1 squared. And then similar for the other components. Now,
So they all end up having a negative.
yeah, well, so because what ends up happening is these squares right here cancel with the squares over here.
Oh, okay, I see.
And then you have
-2.
this -2 cancels with this -2.
But we won't need to know how to derive that though individually,
No,
because that'll be the same.
in the, like, for example, the test,
Yeah,
like, here are two vectors, find the angle between them, which actually is the next example I'm about to do. I'm not gonna give a question saying derive a dot product.
all right.
Yeah, okay. You know, some people who might like that, but. Okay. All right. Oh, any questions before I? When I would teach Cal 2, I would make a really devilish integral. That would require using every single technique taught during the class. Applied to one integral, I'd call it the zinger. It'd be a bonus question now.
That's nice.
Yeah.
Just hateful. It'd be hateful to do all that at once.
The only question on the test.
Yeah.
This one.
You're right, but not product.
And there will be no partial credit given.
No partial credit, it's all or nothing.
I'm gonna be sadistic.
Just long zeros.
Theoretically, the cloud tower should be about the same.
Okay, so that's an example. This is a typical dot product problem. So given U is vector 3 dimensions, 1, -1, 2. B has components -2, 1, 3. Then what is the angle theta between them? Okay. Because even though these vectors sit in 3 dimensions, if you make the vectors, imagine the vectors as 2 sides of a triangle, those sit within a single plane, so we still have a well-defined angle between them inside that plane. So you're gonna use this formula, u dot v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between them. In other words, theta is inverse cosine of u dot v over magnitude of u times the magnitude of v. So just from rearranging this and solving for theta, so this is a good formula to know. The angle is just given by that. But what remains is actually compute all these things that are in this fraction. But to compute the dot product, you'd use the other formula. That's in terms of the components. So what we need here is, okay, the numerator is going to be u1 v1 plus u2 v2 plus u3 v3, and then here we have square sum of squares of all the components of u and B. Okay. So that's what you'd actually have to grind out. Yes, it's ugly. But,
I just wish that U and V didn't look so similar when I wrote them.
yeah,
That's that.
If I use
I ended up
just
using-
like you,
I ended up using a lowercase u for this. Do
that
you think
helps.
that'll be acceptable if I use a lowercase u in my notes?
Oh, I don't care.
Like on the test, I use A
I'm
and
never
B,
gonna see your notes, so. Whatever helps you distinguish.
like on the test, can I use like A and B?
Yeah, I don't care.
Okay,
variables mean nothing as long as you.
I just wanna make sure it's okay.
I once went through a whole lecture using A and Q. And I got to the end of it. And then a student tells me, in a lecture hall full of 200, because it's at Stanford, that they had trouble distinguishing my A's and my Q's.
Oh my God, yeah.
And the thing is, this, for the subject, for that particular subject, using AQ is pretty standard notation. And, because I've had some colleagues that go ahead and change letters, but I feel like it makes everything sound intuitive. So when I cover this topic now, I exaggerate my Q's.
I
Okay,
can also use an uppercase q if you want.
that's probably,
Or no, it's A.
there are other reasons for not doing that, but yeah. Because that's a numerical and algebra class where you use capital letters to refer to matrices and then lowercase letters refer to single entry of a matrix. Although I don't know if my colleagues here follow that practice in 326, but, okay. So let's fill in all the things. Okay, so we have, so first X components, so 1 times minus 2, plus Y components, minus 1 and 1, plus Z components, 2 times 3, and then we have magnitude of U, so that's 1 squared plus 1 squared plus 2 squared. And then for V, we have 2 squared plus 1 squared plus 3 squared. Okay, so the minus 2, minus 1, plus 6. So the dot product of U and V turned out to be 3. And then we have square root of 6 for magnitude of U, square root of 14 for the magnitude of V. And what you end up getting from all this is roughly 1.24 radians. Or 70.9 degrees. Inverse cosine will always give you an angle between 0 and pi, or 0 and 180 degrees. What that would mean is suppose these are your vectors. The angle that you will get is this one. Anytime you range two vectors like that, having a common initial point, is it this angle or this angle? It's the smaller one. Is what this formula will give you. Okay. So this is the formula for angle between two vectors. Dot product you compute using the components. And then you divide that by the magnitudes, and then you take the inverse cosine. Any questions about this one? Okay, pretty much guarantee that something like that's going to be a final exam question. I mean, if you're only going to ask one question about a dot product, that'll be it. Here's some properties of the dot product. First, the dot product of a vector with itself is the magnitude squared. Because if U is equal to, that's components of U1, U2, U3. Take a dot product of itself, it's gonna be U1 squared plus U2 squared, plus U3 squared, so that is a magnitude squared. Dot product is commutative. U dot V is equal to V dot U. Well, I can say that because U and V are real vectors. If they were complex, that would be wrong. Okay. We have a distributive law. U dot product with the sum of vectors is the sum of the individual dot products. If you scale a vector, then take a dot product with another, you can actually pull the constant out. That's one part that seems worth mentioning, but I'll let it go. Any dot product of zero vector with any vector is going to be zero. Because you're multiplying corresponding components. Now, one convenient formula that comes from combining a few of these properties is if I can express the magnitude of a sum vectors in terms of the individual vectors. So we have magnitude of U plus V squared is equal to magnitude of U squared plus 2 U dot V plus magnitude of V squared.
Or you're just distributing it.
Oh,
That's what you.
yeah, distributive law is happening here. So I would use the first property to express this as dot product with itself. And then distributive property. I actually get U dot V and V dot U, but this property says they're equal, so I can combine terms. Using the first three properties gives us this, and then if I were to replace V with minus V throughout, get a similar formula for the magnitude of the difference. Okay. Key concept related to dot product is that orthogonality.
You say that again?
Key property related to dot
Or-
product is orthogonality.
Okay, let's see.
That's a G.
Oh. Or, okay.
Orthogonality.
I mean, it's the same thing as being perpendicular. Why do we stick to this term
Okay,
in this context? Like, I just-
okay, because okay. Orthogonality is really when the inner product of any two vectors is zero, and those kind of vectors could be all kinds of different things. Here in this class, we focus only on vectors in R2 or R3, but So for such vectors, that really in n-dimensional space, we could also say they're perpendicular. But the notion of inner products of vectors of any kind, like for instance, in function spaces and so forth. In that case, we don't really call it dot product anymore, even though we might write it the same way. It's an inner product. And anytime any kind of inner product is zero, we call them orthogonal. Where they might not have a geometric meaning anymore. Yeah.
So if you're going to the higher dimensions or.
Yeah, or other Ricci vector space, yeah. Yeah, because I could say perpendicular in this class. And then you get to another class and see almost the exact same thing. It's like, oh, now we're calling it orthogonal, why? So, okay. So they are orthogonal. If the dot product is zero. But what that means is, but we also have the other formula for dot product. Oops. This dot product, if we keep in mind, it's equal to the magnitude of u, magnitude of v, cosine theta. That means if u and v are orthogonal, and non-zero, that's important. But the only way for this to be zero is if cosine theta is equal to zero. The theta is 90 degrees. So in this setting, where this is the inner product that we're using, if vectors are orthogonal, geometrically, they're perpendicular. So in this class, those two terms can be used interchangeably. Outside of this class, don't. Right. Okay. Now, one thing that you might for two-dimensional space, let's suppose that I have a vector u in 2D that has components alpha and beta. Sometimes, actually, this comes up in Cal 4. Given a vector, you'd like to have a vector that's orthogonal to it. And the easiest way to get that is if I swap the components, the beta, alpha, and then negate either one of them. So I'll negate alpha. Then u dot v would be alpha times beta minus beta times alpha, 0. So u is perpendicular to v or very orthogonal. So this is a convenient way to get a vector that's orthogonal to a given vector in 2 dimensions.
Not let that's a negative alpha, right?
Yes.
Okay.
Yeah, so you swap the components and negate one of them. And that will cause the dot product to be 0. If I were to draw this, so let's
Why would we negate it? I understand I'll give you 0, but isn't that changing it?
well, yes, but I'm trying to get a vector that's orthogonal to this one.
Okay.
So swapping the components, if I just swap alpha and beta, then I would have, okay, so here I have a large y component, so that would put me, let's make sure about this. So just swapping them would put me here, which doesn't give me what I want. They're not perpendicular. But now, if I negate, say, the y component, that would put me down here. This is alpha minus beta, and you can see they're perpendicular. Whereas if I negate the other component, if I do minus alpha and beta, that is also perpendicular to the original. Our usage of dot product is projection. I've given two vectors, u and v. The problem is, what is the best approximation of u by a vector in the direction of v? So if I draw the situation. So here's u. Then here's v. So the idea is I want some vector that's the same direction as v. So in other words, it's going to be a multiple of v. That such that the distance is as small as possible. So this gap between this vector and the dotted one, I want to minimize the length of that gap. So how can I do that?
Make theta 90 degrees.
We do want a right angle. So, and if you're referring to
With the new one.
this angle,
Yeah.
yes. Yeah, so this. So choosing, basically dropping a perpendicular from here to here, accomplishes that. So, so I'm going to call this vector c times v, because c is an unknown constant. It's a multiple of v because it has the same direction as v. This gap between them is equal to u minus dv. Wait. Yes, that's right. Yes, I was cheating a little bit. Okay. So, so to minimize what I'll refer to as the error, which is u magnitude of u minus dv. So u and v are given. It's only c that has to be determined, and c is a constant. Well, I'm going to take a look at the magnitude of u minus dv squared. And using a formula that I wrote on the board some time ago, that would be magnitude of u squared minus 2 C dot product of u and v plus c squared magnitude of v squared. Now, I can think of this as some function of c, g of c, that is this magnitude that I'm trying to make as small as possible. What can I do? Find c that makes this function as small as possible. How do you find the minimum of a function? From your earlier calculus classes. Yes, take the derivative. All right, so g prime of c. Well, this part doesn't depend on c at all, so it doesn't give us anything. I get minus 2 u dot v, that's just a number, plus 2c times the magnitude of v squared, and I set that equal to 0. So now I can rearrange this and solve for c. So c is equal to u dot v over the magnitude of v squared. So that is the correct multiple of v that gives you the best approximation of u. So this leads to a definition, the projection. Okay. It's referred to in the homework as simply a projection. In the notes, which are based on different calculus texts, it's called the vector projection of u onto v. Is as follows. So the way it's labeled in word proj of u with v as a subscript, and the formula for it is, so this is what you use in the homework. This scaling factor is c, u dot v over magnitude of v squared times v. Okay. So for a homework problem, you're asked, here's vector u, here's vector v. What's the projection of u onto v? You work this out, and you're done.
Times v,
Yes, I can do an example on that. Right now.
Where did this last be come from?
Where's what?
yeah, the last v, where did it come from?
Oh, this?
Yeah,
Oh, because, oh, sorry, I just erased it. Okay, no, it's right here. My approximation of u is not just c, it's c times v. So that's, so this v here is that. So this whole thing is my approximation of u. I'm approximating a vector by another vector.
okay.
And v itself was given, I just needed the value of c. I mentioned that if v is a unit vector, meaning that the magnitude of v is equal to 1. And the formula simplifies this a little bit. The projection v is just dot product of u and v times v, because the magnitude of v would be 1, so there's no denominator. And this gets me to a question you asked earlier about the I guess it might not really answer your question, because, that's for interpretation of dot product. I don't know specifically geometric, but what's happening is when V is a unit vector, this dot product, U dot V describes a contribution that V makes to U. If they're orthogonal, no contribution at all. If U and V are in the same direction, then it contributes everything. All right. So as an example, I let U be vector 2, 4, and V be the vector 1, 1. What is the projection of U onto V? Now V, since it has components 1 and 1, the X and Y components are the same. So really, I'm trying to find a vector that has the same X and Y components that comes as close to U as possible. So using the formula, the dot product of U and V over the magnitude of V, but that's squared. And then you multiply all that by V itself. So this fraction is a constant C I was referring to earlier. So we get times 1 plus 4 times 1 over the magnitude of V is square root of 2, but that's squared. Okay, so then we end up with vector 3 and 3. So that is the one vector in the direction of V that comes as close as possible to U. In the notes, I do it a little differently. I make V a unit vector first. I normalize it, so then I can use this formula, but the result is the same. And I don't care how you do it. Okay. Question about this one.
Why didn't you do the cosine formula?
Oh, because, well, for that, we need to be given the angle between them. You said. So, yeah, so here, because we're giving U, V as their components, we should use this one. Yep. Yeah, so either formula is fine, but which one is determined by the information you give it.
Oh, because you.
Yeah. One of my examples from last time was about work being force times distance. Now, I want to give a formula that's similar to that for a case where you don't have all the forces going in the same direction. Actually, let me use the same example. Oh, okay, slightly different numbers. Okay, so we have a box that's being pulled a distance of 10 meters. And the force that's being applied to it to pull it along applied at an angle of 30 degrees. So I have a box on the ground and I have I'm pulling it along from this height. It gives me a 30-degree angle. And this is my force vector. the magnitude of a force is 50 newtons. Okay. Now, since the angle of a force is 30 degrees, that tells me that the actual force vector is 50 times the cosine of the angle between them. The x component, the horizontal component, the vertical component is 50 times sine 30 degrees. Meanwhile, the direction of motion of a box is along the horizontal. So the displacement vector is the vector d that has an x component, horizontal component of 10 meters, and then a vertical component of 0 meters because it's going straight horizontal. So if I wanted to work using the simple formula of force times distance, well, because the box is moving horizontally, I have to use a horizontal component of a force. So that would be 50 times cosine of 30 degrees times the distance that the box is pulled. That's in newtons. And times the distance it's being pulled, that's 10 meters. So what we would get is 500 times cosine of 30 degrees Newton meters. Cosine of 30 degrees is that's 1/2. Wait. Range. Oh, are we numbered? No. Okay, no, it's not 1/2. Cosine 30 degrees is square root of 3/2. Okay. So that's the work done. But if I look closely at this formula right here, the 30 degrees is the angle between the displacement vector and the force vector. So if I look at this here, what do I have? 50 is the magnitude of my force vector. 10 is the magnitude of my displacement vector. And then I have cosine 30 degrees, that's a cosine of the angle between those vectors. But what does this represent? This formula here. Yes. Inner or dot product of F and D. So in general, the work done by force F acting to move an object through a displacement vector D is the dot product of them. So work equals force times distance still applies. Only now, instead of multiplication of numbers, it's dot product of vectors. So if you have your force vector and your displacement vector sharing a common initial point, and you know the angle between them, then this formula will correctly give you the work.
So you can do either way.
Yes. Yes, so then just so the whole class understands what I meant by either way. Or you go ahead and figure out the horizontal component of a force or a component of force that you need and just use this, or just go ahead and do the dot product. Either way you'll get there. So I want you to be aware of that application of dot product. And that happens sometimes. Some formulas so in simple cases like this case where all the vectors involved are going in the same directions, and it's just the ordinary multiplication numbers. We generalize that to a multi-dimensional situation. Is ordinary multiplication becomes a dot product. Questions about dot product-y things? Okay. I think I've come to the end of my notes. Yeah, go ahead. All right. And,
That'll be a good time to stop anyway.
but yeah, I guess it would. So I'll just leave you with one last thought that, since I refer to, dot products, it's synonymous with inner product, or inner product is more general than that. In case you're asking, does that mean that there's such thing as an outer product? The answer is yes. So. But I'm not gonna elaborate now. All right, so next time, cross product. Then you can have two product operations to confuse with one another.
Also, if you ever take physics, prepare to have.
Yeah.
Product L.
Yeah.